Use the integral test to determine whether the following series converges or diverges. Okay, so n equals 1 up to infinity, 2n over 5 plus n squared. Now, if we're going to use the integral test, we need to be working with a function. And that function has to satisfy a few properties. Okay? So f at n of our function needs to agree with the values of the sequence that we're adding up. Oops, no 2 there. So it really seems like f of x should probably just be 2x over 5 plus x squared. Okay, so we'll explore with this one. Now, what do we need? Well, we need it to be decreasing for x greater than or equal to 1. Okay, we need it to be positive, so we'll have to check all of these. And we need it to be, what's the last property? Continuous. And it doesn't have to hold everywhere, it just has to hold beyond your starting index. And even then, there's some wiggle room. Okay. If we found that it wasn't decreasing until x equals 3, we would just work with a tail of this series, and that's okay. Okay, because this series will do what its tails do. Alright, so what do we start with? Well, we could start with positive. For x greater than or equal to 1, 2x is greater than or equal to 2. X squared is greater than or equal to 1, so x squared plus 5 is greater than or equal to 6. These are both positive. So our function is positive. So there we go. Positive is all dealt with. Continuous. Yeah, it's polynomial over polynomial. So it's continuous, yes, because it's polynomial over polynomial. I suppose you should point out that the denominator polynomial is never equal to 0, so we don't have to worry about a discontinuity, a vertical asymptote, or anything. I guess probably should have checked that rather than just saying obviously it's continuous. Decreasing. Okay, this is the one where you usually have to do a little bit of work. Okay, let's differentiate this. Now you don't have to if you've got another argument that will work, but we can just use the quotient rule here. What do we have? 2x, and then the derivative of x squared plus 5 is another 2x. Okay, now, the denominator here is always positive. Okay, so our function is decreasing exactly when this numerator is decreasing. We can simplify it a little bit. Let's say 10 minus 2x needs to be less than 0. Okay, so 10 needs to be less than 2x squared. So 5. Okay, so this happens, x squared is greater than 5. This happens when x is less than negative root 5. Or when x is greater than root 5. Now, root 5 is between 4 and 9, so it's about 2.236, something like that. So we don't actually get decreasing where we want it to be. Okay. So what do we do in this situation? Pack up, go home, integral test won't work? Well, no, they said use the integral test. So what do? Well, we just make it so this condition is satisfied. So we'll say instead, consider the tail. So we'll start with n equals 3 because that is past this point here. And we do have to make sure our integral test is satisfied. Okay. So we'll have the same f of x, but this time it's decreasing for x greater than or equal to 3. Okay, it's positive, again, for x greater than or equal to 3, and it's still continuous. Okay, so the integral test applies. Okay, so what does that tell us? Well, the integral test says, all right, you want to tell if this series converges or diverges. Instead, work out the behavior of this improper integral. And whatever it does, converge or diverge, so will your series. Okay? Now, I have already made a typo. We're starting with 3, and out of habit, usually you start with 1. Okay, but we should be starting with 3. We're working with a tail. Okay. So now what are we going to do? We'll introduce a t. Go from 3 to t. All right, we use limits to help us work out whether type 1 improper integrals converge or diverge. Okay. Now this one here, you can play around with it. It's just a quick substitution. You know, u equals x squared plus 5. Okay. And so this will be 1 over u du. I would encourage you to check it out, make sure I'm not just making things up. Okay. But then we know how to integrate that, so it should be ln u. And then we can switch back. So we can say ln in absolute value of x squared plus 5, but x squared plus 5 is always positive, so we don't really need the absolute value bars. You can keep them if you want, but we don't need them. Okay, and then we're going from 3 to t. Okay, so now we plug in t squared plus 5 minus 3 squared, which is 9, plus 5. We can combine them if you really want to. You don't have to. We're really just interested in the one that has the t in it. But you can combine them. Now, as t gets bigger, t squared gets bigger, t squared plus 5 over 14 will get bigger, and so ln of all this will also get bigger. It'll tend to infinity. Okay? As your input gets bigger, ln gets bigger. It gets bigger slower than its input, but it does get bigger. So this limit here does not exist. So by the integral test, since our improper integral here diverges, the series we were talking about diverges, but that's not the one we were given. It was just a tail. And so if a tail diverges, so does the original series. Okay, so what have we shown? Our given series diverges.